Okay, dear conference participants, please take your seats. So we start our afternoon session of the conference, exploring the energetic cosmos. So, and our first guest speaker in the afternoon session will be Pawan Kumar. He'll be talking about the relativistic jets in tidal disruption events. Please welcome our guest. Thank you.
Thank you. Thank you for the invitation. Pleasure to be here. Pleasure to be here. What I'm going to do, since the audience is mixed audience, it seems like roughly half of you work on high energy astrophysics and other people work on variety of different areas. So this is going to be certainly second half would be slightly specialized, but hopefully accessible to all of you. What the goal here is to certainly talk about some recent phenomena, and I will describe that. But before that, I want to provide a little bit of a background that jets are very common in astrophysics. We see outflows from objects of all different kinds, from newly forming stars to black holes and so on. And I would like to share some examples of that from certain systems. And typically these are systems with black hole. We see an outflow moving at a speed close to the speed of light. So astrophysicists, astronomers call it relativistic jets. Example of that, this one is in our own galaxy. It's an X-ray binary, a black hole, and in orbit with a normal star. And matter is falling from the companion star onto the black hole, and it produces an accretion disk and a relativistic jet. These systems, this is an example of this. This is a radio millimeter data, and that shows the speed of the jet, and that turns out to be moving at a speed which is about 98% of the speed of light, Lorentz factor of about 5. Another example is gamma ray burst, which is death of a star. Bruce is going to talk quite a bit more shortly about gamma ray burst. That's another system. This is collapse of a massive star producing a jet. This is just an example of one of the cases where we have a very firm determination of the speed of this ejecta produced in these in the collapse of this star. The Lorentz factor was measured to be about 7, but that was 25 days after the explosion. Shortly after the explosion, the jet was moving closer to the speed, closer to the Lorentz factor of more like 100 or so. These are just 2 examples of it. There are numerous other examples. Quasars, blazars, they also have relativistic outflow. So these things are fairly common. Few other things, and that is that they are very interesting in their own right as to how the jets are produced, what is the mechanism for launching these jets, what is the composition of these jets, and so on. And that remains an open question and has been around for many decades. Before I get to these questions and tell you about something, another kind of a relativistic jet, first I thought it is worth pointing out that ultra high energy cosmic rays with energies in excess of 10 to the power 19 eV are most likely produced in this relativistic outflow of one kind or another. Not so clear where, but the site is almost definitely one of these relativistic jet. Most of you have seen the data. I'm not going to spend any time on it, but I simply wanted to point that out. The other thing which is very interesting is neutrinos, particularly the high energy neutrinos seen by the ice cube with energies of few tens of TeV to a few PeV neutrinos. These things coming from these are astrophysical in origin, meaning coming from outside of our atmosphere, are also almost certainly produced in these relativistic jet of one kind or the other. I'm simply trying to provide a background information about that these jets are common, but they are also connected with many other things in astrophysics. So with that background, what I would like to do is proceed. First, pose the question. I have already mentioned the question, but I'm going to repeat and summarize that in this particular slide. These questions have been around, as I say, for several decades. And the questions are, how are the high energy photons we see in these jets produced? It could be synchrotron process, synchrotron self-Compton process, it could be something else. How are particles accelerated in the jet? That's one question. And for none of the systems, we have a clear answer to that. What are the jet made of? That's another question. It's a basic question, and we do not know the answer to that for any of the systems that I described to you. The jet launching, many theories, but we do not understand how the jets are produced, how they are launched. So these are some very basic questions that we do not know the answer to. What I would like to do in the remainder of the talk that I have is first describe to you yet another kind of a system which produces a relativistic jet, and then I will share with you that particular system provides insight and can answer some of these questions. So that's where I'm going. That system is the following: that we have supermassive black holes at the centers of most galaxies. Supermassive black hole, for those of you who do not again work in astrophysics and black holes, these are black holes with mass in excess of about 1,000,000 times the mass of the sun. Stars are seen to fall into these black holes, but before they fall, they are tidally shredded by the tidal gravity of the black hole, and they form an accretion disk. In some fraction of these cases, a relativistic outflow is seen, and an X-ray emission is seen. And what I would like to show you, that these systems which produce a relativistic jet, in this process of a star being tidally shredded by a supermassive black hole, are good systems to answer some of these questions. That's where I'm going. So first, a little bit more information as to what's going on. What we are looking at here is a star and a black hole. The star is on a trajectory, almost radial trajectory, not completely radial trajectory toward the black hole, but it's coming. So it's coming toward the black hole, and the arrow shows, and this is the trajectory of the black hole. So as it approaches, the tidal forces increase, the star is elongated in the longitudinal direction, and compressed in the transverse direction. The tidal acceleration, which we all know what that is related to the black hole mass. It's related to the size of the star and the distance between the star and the black hole. 1 over distance, d being the distance cubed. This is the star self-gravity. If the tidal gravity exceeds the star self-gravity, then a star is going to be then stretched and ultimately shredded, torn apart by the black hole. And here is the condition when that will happen. If we take a star such as the sun, then it is going to get shredded by the supermassive black hole outside of the event horizon, as long as the mass of the black hole is something on the order of about 30 million times the mass of the sun or less. If the star is more massive than 30 million times the mass of the sun, then the star is going to fall intact and not be shredded outside of the event horizon of the black hole. So those are not interesting cases. Did I say, see a hand raised? Go ahead. No, just go ahead. No, please.
Stars which are likely to reach, just a second, So stars which are likely to reach a horizon of the supermassive black hole, what kind of stars are what are the what kind of stars are they likely to be? Is there any data about that?
Well,
About their
what
radius?
kind of, meaning in the terms of the property of the star, it's a random process. So stars are in roughly speaking random orbits in this close vicinity of the black hole. And what kind of star they are, most of the stars in the galaxy are like the sun. So the star is likely to be about a solar mass, like the sun. So that's what about their age? Is again like the sun, several billion years of age. So yes, just because those are the most abundant stars, it's just statistics. It's nothing particularly deep inside about that. Yes. So that's the condition. So long as the black hole is less than about 30 million solar mass, you will have the star, if it approaches close enough, is going to get shredded and be ingested by the black hole or fall into the black hole. And that tends to produce, for a period of time, from months to a couple of years, intense flare, very bright transient object. Some information. So such events are seen. And the history, this is just a brief, this is a slide that summarizes all of such cases that astronomers have detected. It goes, well, the overall rate is about one such event is seen in a galaxy such as our own once every 100,000 years. So it's a rare rate. These are rare events, but we have lots of galaxies, something on the order of 100 billion galaxies. So these are not so rare in terms of the universe, our visible universe. History, four TDEs were claimed to be detected in the ROSAT data in the 90s. They were all seen in the soft X-ray band with bright flares. A number of them have been observed by Chandra, XMM Newton, and Swift. 3 of them have been seen by Swift. And those are very special events seen by the Swift. There we know that there is a relativistic outflow, relativistic jet that is coming from these events. Those 3 are the best cases, the most well-studied cases, and I would say firm cases of this kind of a phenomena, a star falling into a black hole. There are candidates, TDE, tidal disruption event candidates that were discovered in optical UV surveys listed here, number of different surveys, where the peak luminosity is something on the order of 10 to the 42 arcs per second, and that luminosity falls off with time over a period of several months. I have already mentioned, but I do want to emphasize this particular point, that so altogether we have something on the order of about 30 TDE candidates. 3 I would say are robust, and all these 3 were detected by Swift. And in fact, the odd thing is that they were all detected within 3 months of each other. They are at a redshift of order unity. They were all detected in the X-ray band and had the property, which is kind of a telltale signal that you are looking at a star falling into a black hole, which I will share with you. But before I share with you that data coming from Swift, I just wanted to point out that these things are very good ways of studying and answering some of the questions that was posed 2 slides ago. The composition of the jet, how are the photons produced, and so on. And the reason that we can answer these things are very good is these are very, very bright, but not exceptionally bright. Gamma ray burst, as Bruce will tell you shortly, are much brighter. But what's very nice about them is that these jets are completely transparent all the way to the horizon because the underlying object is a supermassive black hole, and therefore you can see down to the launching site. So that makes it very different from gamma ray bursts. One of the events, the first one seen by the Swift was, if I can get this thing working, which I'm not sure whether I will be, there is a little movie. Yeah, it's working. So this first event with a relativistic jet was seen by the X-ray telescope aboard the Swift satellite. And this was a case where a star wandered too close to a black hole on March 25th, 2011. And the distance to this object was 3.8 billion light years from us. And the star was shredded completely. A relativistic outflow was produced. And this system, there is a certain telephone number associated with it, which doesn't matter. Though for most of you, you wouldn't care and doesn't really matter. This is an event that turns out can address some of these long-standing questions. Say please again.
Please wait for a mic.
Be so kind, repeat this slide once again.
Can I replay this thing? Is that what you...
No. Repeat once again.
Repeat once again.
Repeat. Yes. Multiplication of this film. I want to see.
Oh, you want to see this animation again? I will try. I will try to see if I can.
If it is possible, of course.
I will try. Certainly. You can see the object, the star being shredded, forms an accretion disk because of angular momentum, and you see an outflow. Obviously, this is an animation. This is not an actual observation. Just to clarify, in case there was a doubt about it. Data. The data is, this is Swift XRT data, Swift X-ray spectrum of this object. So the spectrum was very simple spectrum. It's a power law spectrum with the spectrum is shown here. F nu, the flux per unit frequency, fell off as 1 over frequency to the power 0.8. Light curve, very interesting. Lot of fluctuations on time scales of 30 seconds and roughly constant flux for a period of about a week to 10-15 days, and then it fell off. It had fluctuations that continued, but it fell off, and it fell off as 1 over t to the power 5/3 on average. And that's a telltale sign of a star being shredded and being accreted onto a black hole. That's something that can be calculated, was known prior to the observation in the 80s. And so that telltale sign of this temporal behavior tells us that you are looking at an event that I have described to you. But then something very remarkable happened, and that is this. The flux fell off after about 500 days. So it continued to fall for 500 days as a power law as I have described. But then it fell off by a huge factor, more than a factor of 10, closer to a factor of maybe 30 or 40 over a very short duration of time after 500 days. So this relativistic outflow persisted for 500 days and then just took a nosedive. It completely died out and disappeared. It was seen, that is to say, the data was seen. This is this observation was all of this observation from Swift X-ray telescope, this data point, Chandra. This is Chandra. Yeah, Chandra's satellite. So, yeah, saw that. It was caught by Chandra. It had fallen, the flux has fallen down quite a lot. Uh, this was followed, this SSA was the first event, very famous event, and it was followed by a number of satellites, and there are limits. Fermi followed it, Fermi high energy detector followed it, no detection were made, these are all upper limits. Veritas also followed it, provided only upper limit. It was detected, however, in the infrared, and you are looking at the infrared data here. In infrared, behavior was, yeah, the infrared flux was falling off, and then this was dominated by the host galaxy. There is another event. There are two other events with very similar behavior as the one that I showed you before. So now let me try in the remaining time, and I'm how much time do I have now?
15 to 20 minutes.
15 minutes, okay. So in the remaining time that I have, what I would like to do is I have provided a framework, meaning I have told you unsolved problems associated with relativistic outflow. I have shared with you data for a particular class of object, and I claimed that this particular class of object, which is more recently discovered, so the first event was discovered 2007, so 10 years ago, that this is special and it can shed light and answer some of these long-standing questions, and I will try to convince you of that. The strategy, so this is the goal. The basic strategy is the following. First, I will try to answer the question, what is the jet made of? Is it an ordinary baryonic matter? Is it an electromagnetic outflow or Poynting outflow or something else? That's the first order, like the 0th order question that you would like to be able to answer. And at the same time, you would also like to know how are these photons produced, the X-ray photons that are detected. There is the same problem that repeats over and over again, be it blazars, quasars, X-ray binaries, or microquasars, or GRB. We have this same common problem for all of these systems. So the basic strategy is, repeating myself, assume that the jet is baryonic and follow it through. Look at the consequences. Assume that the jet is a Poynting outflow. Follow it through. Compare, go through the calculations, compare it with the data, and then see which model stands. So by the process of elimination, hopefully, you will have an answer. And that's the strategy. And I will give you the bottom line and go through the exercise. The bottom line is that if the jet were to be baryonic jet, it doesn't really explain all the data that I showed you for the system. X-ray, infrared, high energy data, which means GeV data, and so on. It requires a Poynting outflow, a jet where the energy is being carried by a magnetic field. That's what's needed to be able to explain the data that we have got for these systems. This sketch simply says that we have got a jet coming from a black hole, the close vicinity of a black hole, and at some distance from this event horizon, the energy of the jet is converted into radiation. That's just a sketch of that. And this is something I have already mentioned. Assume it's a baryonic jet, go through the process of calculating the radiation, compare it with the data, and assume that it's a Poynting jet. Again, go through the process of calculating the radiation, comparing with the data, and then determine which of these two explains the data. The main difference between the two processes is that you have got, in the case of a baryonic jet, the energy is in the form of kinetic energy of particles that must be dissipated by some kind of a shock and then radiated away. In the case of magnetic field, you have to convert the energy of the magnetic field to particle energy and then radiate it away, right? And the difference between the two is that in the second case, you could have particles which are continuously accelerated, because in the process of dissipation of magnetic field, you create an electric field, and that electric field can continue to accelerate particles. Whereas in the case of shocks, particles are accelerated via the Fermi process only while they are crossing the shock front back and forth. So that's the difference. That's the main difference between these two. Radiation, once you have converted the jet energy, that is to say dissipated the jet energy and deposited that into particles, you have now many different ways that this energy of the particles can be radiated away in form of X-ray, gamma ray, photons, and so on. And there are numerous processes, and we have looked at every single one of them. It could be synchrotron and synchrotron plus inverse Compton, thermal photons. If these terms are not familiar to you, you can always ask me questions, and I'll be happy to elaborate and tell you more about it, and so on. So the point being that you have got numerous different processes that could be at play, and you look at all of these possibilities and then see what survives. You have observational constants. Those are outlined here in this slide. We know that the flux is varying on a short time scale of something on the order of 30 seconds, so certainly less than 100 seconds. The source clearly must lie outside of the event horizon. That's one of the requirements that must be satisfied. The jet Lorentz factor is about 10. We know that. We have a lot of information from the millimeter, late time millimeter and radio data. That we have that information. We know the luminosity in the X-ray. The isotropic equivalent of luminosity in the X-ray is quite large, few times 10 to the power 47 ergs per second. So whatever mechanism that you appeal to or you look into, it should be capable of producing this luminosity. Moreover, the flux, energy flux below the X-ray band must decrease at least as fast as nu 1/3. Otherwise, it will end up overproducing the infrared and optical emission that we see from these events. So those are the requirements. Those are dictated by the data. And any mechanism which survives must survive, which is to say explain all of these constants that the data is providing. So now I will have a quick rundown of the mechanism, give you a flavor. I'm not trying to give you all the technical details. That's completely pointless to try to give you all the details. But the flavor I will like to try to give you. So assume that the jet is baryonic. Let's assume that the radiation is produced by the synchrotron process. Well known, very well understood process where electrons are gyrating around magnetic field. There is a certain frequency that at which the radiation peaks, the synchrotron radiation peaks. The flux can be calculated, depends on the strength of the magnetic field and the number of electrons in the jet, and of course the Lorentz factor. You can put it all in and ask, given those constants that I described, does this work? The answer is that all of these regions that you see, this is a two-dimensional plot, which is the following. Distance from the black hole is the x-axis. The y-axis is the Lorentz factor of the electron, which is producing the synchrotron radiation. And for wide variety of reasons, all of this parameter space is completely ruled out. I will point out few. I'm not going to go over every single thing here, either because you produce too much infrared radiation, much more than is observed from these events, or there is too much gamma ray, which means gamma ray here is referring to MEV photons and GeV photons. There's too much of that, too much flux in that, and so on, or too much energy is produced. Only a very small part of the parameter space survives, and it's hard to see how that tiny space could really work over an extended period of time of 500 days. Okay, so although in principle that could be the case, it seems not practical to be able to maintain that over an extended period of time. So it doesn't seem to work. you can look at and ask, could it be a synchrotron, which is to say you produce photons by synchrotron, but these are lower energy photons, and then these lower energy photons interact with energetic electrons and boost it up, and the energy of the photon is boosted up. So that's called the inverse Compton process. Could that explain the data, both infrared and also X-ray and so on? Okay, so this is the basic process outlined here in this slide. Same exercise is repeated. What you do is look at this process at work at different distances from the black hole, going down to the Schwarzschild radius of the black hole out to a very large radius. This thing is cut off at 10 to the power 17 because that is the place where the jet starts to lose its energy due to interaction with the surrounding medium. There is a medium that is the jet is interacting with, and it starts to deposit its energy. So it's losing its energy at this radius. So there is no point going any further than this particular distance. This one here, once again, the Lorentz factor of the electron. What you find is that these different panels, 4 different panels, correspond to so-called the Compton Y parameter. Again, if you have not come across this term, it doesn't really matter. There's just another parameter in space that describes the electron energy and the optical depth of the system to Thomson scattering. This shows you nothing survives. All of this parameter in space you see completely killed due to one reason or the other. So this is ruled out. This process doesn't work. Thermal radiation simply is referring to the fact that there is some process by which you produce a photon. It is unprescribed, and then that photons, which is thermal or Planck-shaped spectrum, is then interacts with hot electrons and produces this power law that we saw, or Swift X-ray telescope saw. Somehow that Planck spectrum is turned into a power law spectrum. Answer is it doesn't work. Why? Because the optical depth required to process thermal photon and convert that into power law requires high optical depth. And the optical depth at the event horizon is order unity for these systems. And that was the beauty of these systems, of these tidal disruption events. And therefore, so this process ruled out. You can't do that. Pointing jet on the other hand. So all of these things that are ruled out are for baryonic jet. Pointing jet, where the energy is being carried by magnetic field, works fine. Where what you do is that energy of the jet is carried by magnetic field. These lines are a crude way of showing that there is magnetic field that's carrying much of the energy of the jet. And at some distance from the event horizon, this energy of the magnetic field is dissipated. That is shown here in this inset as a current sheet. This is where magnetic field lines of opposite polarity or oppositely directed magnetic field lines come together or forced to come together. They undergo dissipation, and energy of the magnetic field is converted and goes into accelerating particles, and these particles then radiate. And that turns out that it explains the data. The strength of the magnetic field that you need is modest, something on the order of less than 100 Gauss in the co-moving frame of the jet at a distance of 10 to the power 15 centimeter, or something on the order of 1,000 Schwarzschild radius. So modest field. However, electrons are accelerated to Lorentz. The electrons are accelerated to Lorentz factor of 10 to the power 5. Protons to much higher energy, something on the order of 10 to the power 18 electron volts for this particular event that I described to you. So these could be still potential sites where ultra high energy cosmic rays might be produced. Seems unlikely. There's just not enough energy in these events. But an analog of these things could produce ultra high energy cosmic rays. I'm going to skip this one. And what I'm going to do is provide a summary. And the summary is that we have in the last 10 years, and particularly in the last several years, we have seen a new class of relativistic jet. These are produced when a star falls into a black hole. And that has provided quite a lot of information about long-standing open questions. A fraction of the energy of the star is converted into radiation in this process fairly efficiently. Something on the order of maybe about 5% of the energy, rest mass energy of the star is converted to radiation. Piecing together the multi-wavelength data from millimeter to gamma ray, what we have concluded is that the jet that is produced in these events is carrying energy via magnetic field. Magnetic field is the carrier. The baryons, ordinary matter, electrons and positrons for that matter, only carry a small fraction of the energy of the jet. Of course they are there because you do need current to support magnetic field, but they are not the dominant carrier of the energy of the jet. The magnetic field in the jet is dissipated at a distance of something on the order of 10 to the power 15 centimeters, something on the order of 1000 Schwarzschild radius, and that's the story. Two quick things. Do I have 2 minutes? I have 2 minutes. I would like to share with you two other interesting stories very briefly. One of which is that last year there was a paper here by Kara et al. That found that there is an iron line in one of these tidal disruption events. That line here is shown. Iron line could be produced. So we worked on this thing. My student Wenmin Lu and I worked on this thing, and Julian Kralik, very important. Julian Kralik made a very nice contribution also at Johns Hopkins. And the model that we have is the following: that X-rays are produced in the jet by the process that I described, and these X-rays are beamed to within 1 over the Lorentz factor of the jet. So some fraction of the X-rays leak out from the jet and impinge on the surrounding medium, which is wind from the accretion disk, and they are processed and produce these iron K alpha emission lines. That's what is seen. Final thing, the very final thing, in the remaining about 1 minute, I will make sure that I do that in 1 minute. These X-ray photons, soft X-ray photons, and the UV photons that are produced, we predicted, Wenbin Lu, my student, and I predicted about a year ago that these photons will be absorbed by dust in the surrounding medium. These things are occurring at the centers of galaxies, which are rich in gas and dust. So they should be absorbed, and then the dust will re-radiate the radiation in the infrared. So we made that prediction as to what that should be. That particular part of calculation, these are all published. So if you are really interested, you can follow the details. But let me just show you, we predicted what it should be, what the behavior of the infrared should be. It should last for something on the order of a year or so. We provided the spectrum and so on. And lo and behold, within few months of the prediction, this thing was observed by a number of different groups of people for a number of different tidal disruption events. And that's what the last thing that I want to share with you. You have the dust radiation, re-radiation that is seen here. That was picked up by a number of events with the property that we predicted, with the spectrum that consistent with what we had. And I have used up the time. I will leave the summary slide up here and then take questions. Thank you.
So, thank you. So do we have any more questions? Sure.
Working? Just some common question. what is a typical magnitude of magnetic field of black holes, which you consider?
So,
And do your results depend on this magnitudes or not? Because I try to find some formulas and with magnitude of magnetic fields and so on, but how your energy of jet depends on magnetic fields.
I understand
Thank you.
Yes, it is determined self-consistently. We make no assumption regarding the magnetic field strength. What we do is that magnetic field is an unknown quantity. We have no knowledge about that. But we do know that this is producing X-ray photons. Therefore, we link it to the synchrotron radiation. Synchrotron radiation, the photon energy depends on the magnetic field strength, and it also depends on the particle energy. Hence, you saw that two-dimensional plots with electron energy and the distance, and so from there, the fitting of the data. We make a determination of the magnetic field strength. And it does depend on the distance, but that is also determined self-consistently by other constants, infrared, GeV, and so on. So these things are all put together, and the strength, again, I'm repeating the result that I showed you, 58 Gauss at 58 Gauss in the co-moving frame of the jet. The jet is moving with a Lorentz factor of about 10. Therefore, in the lab frame, the magnetic field strength would be 10 times larger. So something on the order of 500 Gauss. Yes?
I want to say you that there is direct relation. I'm continuing the question of Professor Sushkov about the magnitude of magnet field of black hole. You must know the direct relation between angular momentum from one side and the other side magnitude of magnet field that produce this black hole. They are related each other, omega and B. In principle, based on these results, you may get more precise estimation of your results. Is it clear?
Please keep going. I mean, I'm looking to see that there is a question somewhere in there. So
no. I'm talking about the magnitude of magnet field.
Correct.
Yes.
Does it depend on the spin of the black hole?
Yeah, sure.
No, it doesn't. The magnetic field strength and the black hole spins are not correlated. They are two different processes. They have, in principle, nothing to do with each other.
They are correlated. I believe this.
Sorry, they're uncorrelated.
I believe this. You said that there is no correlation.
There is no correlation.
But I think this is direct correlation between themselves. This is yes.
So probably we can postpone it for
no. So be so kind. I have another question. When you talk about the shock waves, did you consider the adiabatic gigonio? Because in this case we have the process of changing the equation of state of this wave, and it is necessary to take into account also.
That's right. Equation of state will change because you start with a subrelativistic equation of state. It's a cold jet which is undergoing this shock, and the shock gas is relativistic, and therefore, yeah, sure, there is a change of equation of state in that process, and that is very much considered in a self-consistent way. So that is
another equation of states that described by adiabatic gigonio.
That is correct.
So, any more questions?
I have a question, or I'll start a question and we can talk about it later. And that is, we were talking about the fact that some neutron stars, which are not so different black hole, have their pulses made up of many micropulses. And you're saying these are current sheets going out, but what makes the current sheet a stable thing? Why do they have to be large compared to the black hole? Can't they be small? And aren't they, the magnetic field is being twisted up, does it break off and reconnect and send out current sheets, or are you having a coherent current sheet go out? I mean, you only have to violate your one thing, which is large compared to the size of the black hole, and then you can make some of these other mechanisms work. But certainly the magnetic transport could carry the energy out. But what's the configuration of the magnetic field? Can it be broken into many small pieces?
Probably
and
is.
just seeing the average out? And do you have any data there on the polarization to give you some indication of the structure?
For none of these systems, unfortunately, we have any polarization information in any of the bands. Not in X-ray, not in optical, not in, so that information is not there. But the first part of what you say almost certainly must be the case. And we know that to be the case because we see fluctuations. We see the light curve in the X-ray band is fluctuating on a time scale of 30 seconds. That suggests that it is not in a smooth continuous flow, but it is undergoing a lot of fluctuations, which could be due to the process that you described.
I'm thinking much faster.
It could be even,
but it can be bigger modulations.
It could be also possible that 30-second is, much of that is limited by the instrumental resolution. So it is entirely possible that it could also be varying on a shorter time scale that we are missing out. We are simply averaging out. But the perhaps other sense of your question was an analog of this to the thing that you were mentioning at lunch, which is these nano flares from Crab. And that system is that is producing is clearly much smaller than the size of the neutron star. Much smaller than the size of the neutron star. Same thing probably applies here. Not the same as in the same physics applying here, but size-wise. What is producing these jets is a region of size smaller than the size of the black hole in the terms of event horizon.
So, okay, thank you. So if there are no more questions, so let's thank the speaker again. So thank you. So, and our next speaker is Bruce Grassan, who is the one of the main principal investigators at the Energetic Cosmos Laboratory. So please welcome. Oops.
If there isn't a little traffic jam here.
Yeah, sure.
Get the show on the road soon. So thank you very much again for giving me a chance to speak about projects that I'm very excited in. I'm from the Energetic Cosmos Laboratory. Is this still on? Is this still, can you hear me? Yes, okay. I'm from Energetic Cosmos Laboratory, and I'd like to remind you that I've had collaborators who helped me with a lot of this work, including George Smoot, Eric Linder, my student Magjan Kistubayev, and many others who have worked with me on gamma ray projects over the years. This is sort of carrying through. So for those of you who don't remember or know about gamma ray bursts, I'm going to tell you a little bit of the basics, especially for the students here. And this talk is almost exclusively about long type gamma ray bursts. We have another talk later today about short type gamma ray bursts, very different animal. So this is what a gamma ray burst is. It's the little squiggles you see from orbiting spacecraft like the Swift that are the energy from hundreds of keV to many GeV. But they typically look like this. They're squiggles. They're very violent, fast events, and they look very different. Every one seems to be very different. The only thing that these have in common is that about 90% of their flux happens in more than a few seconds, which is why we call it a long gamma ray burst. These long gamma ray bursts typically happen when you go back and look where they happen. They typically happen in star-forming regions, so we know that they're associated with star-forming regions. And their typical redshift, these will be galaxies at around a redshift of 1.5 or 2 typically, but up to extremely high redshifts. In fact, they've been detected to up to a redshift of 9. Which is just astounding in our business of astrophysics, looking deep, far back into the history of the universe. They last milliseconds to hours, although these hour and ones are very rare. They've been measured up to GeV in the lat, the Fermi lat, and their long type gamma ray bursts are sometimes associated or sometimes shown to be massive star collapse supernovae. And so you have here gamma ray burst 980425. Well, later it turned into supernova 1999 BW. So we know there's an association of these with supernovae. I like to call these the great cosmic mystery. Eric talks about the beginning of the universe as the great cosmic mystery, but I think these are very exciting because they're the universe's most energetic explosions. They're so bright they can be seen even back beyond the time of the first stars. You take those brightest gamma ray bursts, you push them back to a Z of 12, ridiculous. Before the first stars even, you could still see them because they are so bright. And this means that they are interesting as possible probes all the way of all the space and matter, all the way between us and this great redshifts that they occur on. But you can look up papers, very detailed models of these explosions, of the jets as something that Pawan was talking about, gravitational wave emission even for type 2 bursts, but the emission mechanism remains unknown. This is very simple. You ask somebody, what is the emission mechanism of a gamma burst? They're like, well, it could be this, well, it could be that, well, it could be that. Well, that's pretty, that's pretty weak. I want to get further in understanding these bursts. Let's talk about the cartoon picture of bursts. We have this idea that there's this thing collapsing and becoming probably a black hole. And it forms a jet, as Pawan talked about. And then you have inside the jet, you have collisions between different accelerated lumps of matter, and they start hitting each other, and then they have these bursts, these squiggles that you saw on the plot before. There can also be a reflection between these and an internal shock, and eventually this jet hits the external interstellar medium. At that point, we call it an external shock, and this is what we call the afterglow. And so this is very short time scale emission, and this is longer time scale emission. And I think my laser pointer has just died, if we have another one somewhere. So gamma ray bursts are so bright and variable because of this relativistic jet. And if you're viewing the jet, looking at the jet, then you see incredibly bright emission that can be discovered at this extreme distance. Our crack crew here is fixing my laser pointer, and hopefully we'll be able to do this. Okay, so I want to talk about just the afterglow of a gamma ray burst. It's very important that you understand the difference between the afterglow and the prompt emission of a gamma ray burst. Prompt emission is what happens while the gamma ray instruments detect the gamma rays. But after, we have this very long decay curve, which lasts weeks. So you can put your telescope on this and integrate and integrate and integrate. And so you get these nice long decay curves. And they're very simple. They're just a power law. And their physics is very well understood. It's the interaction of the shock wave with the interstellar medium. It becomes eventually a Taylor-Suttoff solution. Okay, it's very simple. Okay. And these optical afterglow measurements are very common. You can look up catalogs of hundreds of them. Okay, and physics is well understood to be an interaction with the interstellar medium. Okay, but prompt measurements are a completely different thing. Okay, hundreds of gamma ray bursts have been observed in the gamma ray and X-ray bands. Hundreds of afterglows have been observed. Okay, which has to do with the ISM, the interstellar medium, but not the burst emission. The burst emission in the optical is rarely observed, and that's what tells us the physics of the jet. Okay, and it's almost always less than 100 seconds. And here's what I mean by almost always. The duration of these gamma ray bursts is this distribution, okay, discovered by Batsy. As you can see, there's almost none past 100 seconds. And these are the short gamma ray bursts, and these are long. So think of the time scale of this as 40 to 60 seconds. And other than that, it's rare. Okay? Well, if you have a phenomenon that takes place in 100 seconds, you have to be able to point and look at this and record stuff in a time scale very small compared to 100 seconds. If you've ever been to an optical observatory, I'm sorry, even the best optical telescopes, they take hundreds of seconds to move across the sky and point at something. So you're never going to observe these with a conventional telescope. Okay? So that's really right there. It tells us that these are very hard to observe. There are, however, specialized instruments that do observe these gamma ray bursts during this prompt emission. They've done really fantastic work. And for example, the master net and, well, actually, before I get to that, I want to talk about very large field instruments, which just sort of stare at the sky or kind of point in a vague direction. So those have done very exciting work, which I'll show you soon, things like pie of the sky and Raptor. But because they have a large field of view, they put a lot of background into a single pixel, and so they have very low sensitivity. 10th magnitude. 10th magnitude is an extremely bright astronomical object, and it's rare that you can measure much of anything with that. There are medium field, very fast moving instruments. One of the most famous examples is the ROTC instrument. Another excellent example is the MasterNet instrument, which is a Russian experiment. And the ROTC3 instrument, a 45 centimeter aperture, has a sensitivity of almost 17 magnitudes in 10 seconds. I use the time scale in this talk of 10 seconds because 10 seconds is small compared to 60 seconds. That's all. Nothing very fancy about that. But of all these experiments that have measured prompt emission, never, not one, there is no operational simultaneous multicolor instruments. That means we know that there was a flux, okay? But what's the spectrum? No measurement, never done, okay? Note that filter wheels, the conventional way of making multicolor measurements in astronomy, are totally useless for this because you have a filter wheel and you take a measurement and then you move the filter wheel and then the gamma ray burst is gone. Or the gamma ray burst is doing something completely different between the time you have one filter and another. Totally useless, have to do something else. Before I go on and give you more of the simple picture, I'm going to be honest with you. Gamma ray bursts can be a little bit complicated. There can be at least 3 optical peaks. One for some kind of prompt optical emission. One for some kind of early external reverse shock, the kind that was proposed by Mészáros and Rees and Piran and, thank you, sorry, and Piran. Thank you very much. Okay, and so, and then of course, you can actually have an afterglow that peaks. Although that's rare, they're usually declining by the time we get to them. By the way, I hope I mentioned that flares have been ignored in this talk. Okay. So either of these two could be subdominant and not seen, and we don't really know that yet because we haven't really probed deep enough in sensitivity. Okay, so what does the best available prompt data look like? Okay, in the time that I talk about this slide, you're going to see a film of an actual gamma ray burst, and it's going to get bright, and then it's going to go away. There it is right there, getting bright. And over here on this plot, you can see the trace of the X-rays, or X-gamma rays, and the optical. Okay. This is a burst called 080319, and another burst called 080319A was going off in the sky right around there, and then just a short time later, 080319B went off right nearby. So many telescopes were already pointed the same place, and we were just lucky enough that they were already there, that there was good weather, and so we got these incredible, beautiful light curves. Okay? We are lucky because most telescopes could not possibly get this. Okay? It was incredibly bright. It was almost bright enough to observe with the naked eye. It's called the naked eye burst. Okay, so we have this amazing light curve by the Tortora instrument, which is a wide field instrument, which is normally not very sensitive. It's actually a Vidicon. We have detection by pie of the sky, another very wide field instrument. Okay, and these are not sensitive to any but the most exceptionally bright gamma ray bursts. And to rub this in, there are nothing like this. In 12 years of operating the last instrument that locates gamma ray bursts, well, this is it. That's all you get. There's one that's close, and then there's nothing else. Here's the other. So first, let me talk about the light curve a little bit, and look how beautiful this light curve is. There's a model for this gamma ray burst where there are 2 components, sort of 2 rather separate emissions. One to explain the extremely bright optical, okay, and one to explain a sort of different decay slope at the long term. It's an interesting model. It's very well respected. It's not unique, but it seems pretty reasonable. Okay, and I want you just to remind you, look at how this optical comes up, and it maybe has some features in it, and comes down, and it maybe looks like the gamma rays, and maybe it's on the same time scale. I also want to make you notice how incredibly fast this drops after this prompt emission. Zoom, drop, zoom. Okay. Look at this beautiful time resolved data we have in the optical. Okay, it looks like the X-rays in black are sort of two humps, and it looks like the optical is also two humps. Now in detail, maybe not. Maybe not a real correlation, but in gross detail maybe. In gross detail maybe there's some kind of a delay. I don't know, but boy, I'd like to see more of these and more data to work on this. I'd like to show you the spectrum in 3 time periods. Okay? These 3 different colors will tell you about 3 different time periods during the burst. These spectra are fit here by what's called a band function, just 2 power laws, very empirical kind of approach. Look at how incredibly rich this data are. Look at how many little tiny error bars that you can put on this line and how much fitting you can do with these data. I mean, they're really beautiful. Unfortunately, there's just 1 point in the optical. That's it. That's all you get. You get hundreds here in the X-ray. You get 1 in the optical. What are you going to do with that? Notice also, and so what about here? What is this doing? Does this thing go like this and then jump up to the optical, or does it come down slowly all the way? What is going on? And one other thing I wanted you to notice is that this is an absurd miss of the extrapolation. In fact, it is 1, 2, 3, 4. What is it? 4 orders of magnitude off. I mean, that's incredible. So something is going on in the optical that these spectra do not tell us about. We need to know more about this optical emission. So here's the only other sort of really rather good, but nowhere near as good example is 130427A. Here's the optical data. The optical data, you see this kind of flash, this kind of brightening, and then quick fall over with this characteristic time scale. And then you see some part of this gamma ray data sort of matching, but not quite in this model. Okay, so the point is that there's a big peak in the optical, and there's no such peak in the gamma rays. Okay, so these are clearly uncorrelated, completely different from the other one. And so you know this is going to be a hard problem because 2 gamma ray bursts look like 2 different gamma ray bursts, and if you had 10, they'd probably look all different as well. In this model by Bertrand et al. In 2014, reverse shock dominates the first 50 seconds. Okay, and then it has this characteristic minus 1.7 time decay. Okay, and that's why you say it's a reverse shock. Okay, but this is not a unique fit. There's parts of it that just aren't fit. Okay, and we know that this is a baryon-dominated jet because this optical is so bright. A baryon-dominated jet will give you bright optical, and a magnetic dominator will give you less. Okay. But there's no spectrum in the optical to confirm that this is the right model. And as parts of the model aren't even fit, you have to kind of shrug your shoulders and wonder what's going on in the optical. Can we please have better information? Here's some other famous correlations. Maybe probably a pretty good correlation, although ridiculously limited time resolution. Okay, and this probably not a correlation unless there's a delay. Who knows? Just give me better data before I can really say much about this. Okay. Another thing I want you to know about gamma ray bursts is that most gamma ray bursts are extinguished, something that is generally not appreciated. So most gamma ray bursts have very little optical emission and just have no detection by the optical instrument on the SWIFT satellite. So the SWIFT satellite just goes and it looks as long as, again, it just doesn't see anything. Okay, but virtually all gamma ray bursts have infrared emission. This is great work done by my colleague Dan Hurley, who looked at a bunch of gamma ray bursts with deep infrared imaging afterwards and found, oh, all the ones that he looked at, in fact, had infrared emission. And so this is consistent with this idea that there is about 0.3 magnitudes of extinction, typical, and the range is about half to 5 magnitudes. Now, this is important because we're not talking about 100 magnitudes. We're talking about 5 magnitudes in V, which means in the infrared, where the extinction is about 1/10 as much, no problem. Okay, and that whole picture holds together. So if you cannot study extinguished GRB, GRB stands for gamma ray bursts, I don't know if I ever said that, you will have some kind of a bias against the more extinguished ones, and you'll be missing lots of them. That is, your rate of discovery will be very low. Okay? If you can detect them, you'll have a boost in rate of about 1.6 times from our numbers looking at this extinction in our 2014 paper. Okay, so what does recent work on gamma ray burst spectra look like? So I'm going to show you a very complicated plot now, and you don't have to understand all of it. But this is 110205A was a almost 300-second burst, 260 seconds. And it was observed not just by SWIFT, but by a very high energy sensitive instrument, Suzaku WAN. Okay, and this has a suggestion of photospheric emission. It did not look like that other triple spectrum I showed you. It also had a detection by the SWIFT optical instrument during the gamma emission. Very, very, very rare occurrence, only possible because this was so long. Okay, and what is seen, which is really interesting here, is that the highest energy gamma rays look a lot like the optical. In fact, they look much more like the optical than the SWIFT bands. Okay, and that's kind of what the interesting thing and the basis of this paper is that in his model, he takes and decomposes this into 2 thermal power laws with cutoff, 2 non-thermal power laws, there's no such thing as a thermal power, 2 non-thermal power laws with exponential cutoffs and this thermal photospheric emission. And he makes these models and he shows, you know, look, they look much better than this kind of band function model. Okay, and that's very interesting. And in clearly the key to this paper is reducing data with the optical at the same time. So you have optical, you could do much more fitting is what this slide really tells you. On the other hand, I look at this paper a bit critically, and I'm saying, very interesting, very nice, these spectral components, very nice. This is the spectrum. And they say, well, we have hundreds of channels here to fit, dozens of channels here to fit, a handful, a dozen channels here to fit. 1. All the way in this entire section, 1 channel. Okay, I want a spectrum in here. I want to know if that spectrum is right. That's the way to get rid of this model or to verify it. That would make a huge leap in figuring out these emission mechanisms. Okay, so finally, let's get to talking about emission mechanisms. There's this standard ISS, or internal shock synchrotron model, which has a log slope of about 1/3 in this region, in between the sort of low energy gamma rays and the optical. Equipartition roughly gives the correct energy of the peak emission in this model, and that's why it's sort of a success, and you look at it as a very positive thing. On the other hand, you would have to look very hard for gamma ray bursts that had a precisely 1/3 spectrum. Okay, the actual distribution of slopes is actually 0.1 plus or minus 0.35. You can find 0.8 and you can find minus 0.6, no problem. Okay, so you can't tell me there's a physical law that the spectrum has to be a plus 1/3. It's not right. Okay, and then I showed you that the optical is very, very far above the extrapolation. Okay, maybe there's probably other components or something else going on. The most recent fits are sort of making more complicated electron energy distributions like this Maxwellian thing, and they still don't agree whether or not synchrotron can be a viable emission mechanism. So my conclusion is not about the details of these models, but really about the fact that there's just no consensus on what is the emission mechanism. And so give me more data. So in case you don't believe me, here it is in black and white in the Shen and Zhang 2009 paper. If multicolor photometry near the optical band exists for the same time interval during the prompt phase, it would tell you which of these various cases of the theory would be the one. It would identify the emission mechanism, okay? And in addition, in this paper, they talk about how much information is encoded in finding spectral features, which I'll get to in a minute. Okay. So, are you near the extrapolation down to optical frequencies of what's going on in the X-rays? Okay, do they look like it's just this extrapolation or not? Or is it something more complicated? You can tell this if you have a detailed optical spectrum. The optical and gamma correlation in time, like we saw that beautiful trace for the naked eye burst, are they the same or are they very different? Because if they're the same, it's a very clear argument that they're produced in the same process at the same location. Okay, so you want an instrument with high time resolution, not just the spectrum as I've been talking about. Okay, and you want the slope, the spectral slope within the optical infrared region, because that will tell you the mechanism in the optical component and see whether it's different or the same or what its relation is. Okay, again, the self-absorption frequency, a feature down in the region of the optical infrared, encodes a great deal of information that is in the Shen and Zhang paper about the electron thermal Lorentz factor and even the radius of emission. So we're going to tell you how far away this is from the source, and that's just very exciting to be able to sort of map the jet in this sense. If it's not synchrotron, if it's photospheric emission, it will tell you the thermal Lorentz factor and about the energy dissipation in the jet. So again, this is from one model. There are many different ones. This is from, I think, Piron's explanation. If you have a 1/3 slope here, you have this drastic change in slope here over to nu squared, and that's this nu A, this absorption frequency I'm talking about in synchrotron self-Compton. Okay, so I have a simple experimental goal here. Okay, for a burst sample covering a wide range of properties, so we can understand gamma ray bursts because they all seem to be different. Let's measure the optical and X gamma ray light curve correlations in time. So let's have a nice time resolution on this measurement, and let's measure broadband optical spectral shape, including this kind of absorption frequency. Okay, it's not possible with current instruments. You're limited by time resolution. You're limited by these non-simultaneous measurements. So, how can we do this? First of all, as I mentioned, there's the SWIFT satellite. It's working right now. It's looking for gamma ray bursts, and it can tell me where they are, tell me the position. So when there's a burst, it radios the position to a ground tracking station, which gets onto the internet via the GCN, and it comes to my telescope. I think I even showed the same slide in my other talk, sorry. If you're fast and can look at it with simultaneous colors in your camera, you can do this, all these measurements that I talked about. Okay. Do we have technology helping us since the ROTC and MASTER programs? First of all, we have faster telescopes that are just better direct drive computer controlled telescopes. They're much faster now. Second, electron multiplied CCDs allow for very high time resolution, but with the high quantum efficiency that you get with CCDs, something that we never had before. Previously, we had to do microchannel plates, which have terrible quantum efficiency. Okay, so I went and I found a telescope, and I went and optimized it and worked with some engineers on this, and we got it anywhere on the sky in 8 seconds. You can move across the entire sky in less than 8 seconds. So for a 60-second gamma ray burst, moving across the sky in 8 seconds, maybe you wait 1 or 2 seconds for the signal. 10 seconds, you lose 10 seconds out of a 60-second gamma ray burst, you're good. Okay. This is a nice telescope because it has 2 different ports that you can put instruments on, and you can be looking at all sorts of things with your other instrument, and then when you receive that alert, then you can just flip the mirror and go to my instrument, which is this special multicolor instrument for this purpose. Okay, here's my crude design, and it sort of explains how you make a multicolor instrument with dichroics. The light comes from the telescope. There's many multicolor instruments like this now. Light comes from the telescope. It reflects off this interference filter dichroic, and the bluest part reflects off. You put a little filter in it, and now you've got the blue filter camera. It goes to another dichroic, and the same process. The bluer light gets shaped by a filter here, and now you have a red filter camera. The rest going through to an infrared filter. Now I'm using H-band. Okay, and again, this is sort of the geometry we're looking at. I'll show you a more detailed design here. I call this the Beastie, the Burst Simultaneous 3-Channel Instrument. I'm using the typical Johnson-Bessel B, R, and H bands. The B and R bands are these EMCCDs. If you would look at the telescope and see a camera on this side port here, the light comes out this way. That's the light here, comes off of this dichroic, it goes into the blue camera. Off of the next dichroic, it goes into the red camera. Not shown are a couple of mirrors that take this beam and bounce it over here and then back into this infrared camera. Okay, so you have an EMCCD in the red and blue for 2 separate, independent, very high time resolution signals. Then you have an H-band camera with an H2RG Mercatel sensor. And as are just well-known infrared cameras, we have a cold stop and a cryogenic cooler to make it very cold and very low noise. And this third infrared channel will deal with those extinguished bursts, so you can measure them. I should mention that the final mechanical design of how to mount these cameras, how to allow them to be independently focused, and how to make it weigh not too much is going to be done by Professor Spites of Nazarbayev University Engineering. So very nice that we have this collaboration and good people here to help us with this. We have had a full ray trace done by El Sher, and we can show that in all these bands, we are in fact diffraction limited. For those of you who are interested in astronomical instruments, we get to do this trick because each camera will only be looking at a narrow band. Why do we need an electron multiplied CCD? Each pixel signal is multiplied before the readout by factors of hundreds or thousands. Okay. And this is how we can take 300 millisecond frames is what I find is ideal for this camera setup. These tiny, tiny, very short frames, and take those frames and have no noise penalty, no read noise penalty. With a conventional CCD, every time you read out the CCD, you get more noise. And so if you had to add up all these very short frames to 10-second or 50-second exposures, you would be killed by the noise because you'd have it so many times. Here, there's no penalty, and you can look at the tiniest amount of time or co-add many frames for very sensitive long measurements. Okay, and the beauty of this is it's the same quantum efficiency as the CCD for most of the band, over 90% or 95%. And these are 1024 devices and 13 micron pixels, and we'll get at least 6 magnitudes of dynamic range out of this, even though it is this kind of a EMCCD. Okay, so now, using real numbers from real telescope runs, not the theoretical, we think we can get 21 mags in B and 20.6 mags in R in only 10 seconds of exposure time. And then 17 mag in H in 20 seconds. Clearly we'll have much better time resolution here. H-band is very challenging. That telescope I showed you was a 700 millimeter aperture, not the biggest, but very fast and certainly good enough for this. This is assuming a Kit Peak-like sky, and your actual performance will vary depending on how good your sky is. So can we detect prompt gamma ray burst emissions? Are we sensitive enough? So in my 2014 paper, what I said is the only data we have on this that's very systematic, that studies a lot of gamma ray bursts on the brightness, the early brightness of gamma ray bursts, is to look at the data from the optical instrument on board Swift. Now, it doesn't catch all of the prompt emission from gamma ray burst. It catches something like the end of the prompt emission and the beginning of the afterglow. Okay? But what this tells us is if we are sensitive enough to catch the end of the afterglow, we are sensitive enough to know if there's bright optical emission before. We can at least answer the question, was there bright emission? Answer, yes or no. In this case, we see that the faintest ones are actually around 19 in W, this crazy band by the Swift, which is more like 20 in red. Master is sensitive to about 10% of these. ROTC is sensitive to more like 50% of them. And Swift, which is where I got this distribution from, of course, sensitive to almost all of them. in 10 seconds, okay? But our telescope comes in over here. We'll be able to be much more sensitive than the early emission from all of the gamma ray bursts measured in 10 seconds. And so that's very exciting. And the reason is just that it's a pointed instrument with small pixels, unlike previous instruments. So unfortunately, Mother Nature is cruel because they have things called clouds. They also have things like snow and rain and braking instruments. So if I scale my sensitivity to another instrument that was dedicated to looking at gamma ray bursts from essentially the same scheme, the ROTC, if I scale this, I believe that I will see, very conservatively, 4.5 detections a year in all bands. In the infrared, however, you'll see 7. Why? Because so many of them are extinguished. So this is the full extinguished, including the tails, and this is just in the optical. Okay? And so for all of these, we'll have a very sensitive measure of whether or not there is this emission. Okay? And again, we expect this boost in detection rate by 1.6 for at least getting the infrared value. Unfortunately, the uncertainty in this is not dominated by my playing fast and loose with numbers. It's dominated by weather. Okay? You have a bad weather year, you'll have a lower number. Now, astronomers like color diagrams, and we have a logarithmic measure of flux called a magnitude. And so we have a R minus H value and a B minus R value. And what this amounts to is just a ratio between the bluest channels and the reddest channels. Okay? And it's just telling you what's the slope in each channel and then plotting it in a two-dimensional space. And what this shows you is that at a slope of minus 0.33, you would get this result, slope of 0.33, slope of plus 0.67, and so forth. Okay? But if you have no absorption, you clearly separate all of these slopes. But if you had an absorption feature that was somewhere in between the two red bands, depending on where it is, you would still be able to determine the slope and the location of that absorption feature, and that will give you the radius of emission, and that will be really wonderful. But just to remind you, again, what this looks like, this case here is for all the bands above this absorption frequency. This case here is for close to 1, right near it, and this case here is far away so that it's really dropped off. But again, what's so nice is that we have this two-dimensional plane, and we can really use this to really figure out what's going on and make a nice measurement. I'd like to give a little shout out to my student, Marjan Kistubayev, who is working on our photometry and making sure that I promise this stuff, but I can really measure it. There's another thing I'd like to talk about, which is very exciting about having the infrared channel, and that's dust emission and dynamic dust. Okay, dust absorption. I think I said dust emission. I meant dust absorption. Imagine that you have a star here, and imagine that it explodes and it's burning a hole through this dust because there's so much X-ray and ultraviolet, which evaporates dust. Okay? As you burn the hole at a finite time, as you burn away the dust, there's less extinction. So what this means is that if you have an infrared channel, you'll see the emission come up. Okay? But if you have a blue channel, it'll be completely absorbed in this early time. And later it'll become brighter, like the infrared channel. The time scale for this process is in fact about a minute, about the same time as a gamma ray burst. So during the gamma ray burst, you can watch this dust absorption dynamically. So we'll just look at this ratio in time and see it happening. So that's very exciting because it solves what's called the excess gas absorption problem. There is a lot of X-ray absorption in these systems that are seen at late times with no optical absorption. Usually dust and gas come together, but not here. Well, what if you have something burning away the dust? It solves the problem, okay? So we need this time-dependent spectral slope to do these measurements. But what's really incredible and exciting to me is that you see the difference only in the local dust of the star. In other words, you're studying dust around one little star in a distant galaxy. There's no other way that I know of to separate the measurement of the dust in the disk and around the little star. So a way to study chemical elements around very distant stars, I think is very exciting. Of course, to measure the extinction, it's a very simple matter to just, with any reasonable extinction curve, to simply look at the ratio between an optical band and an infrared band. Simply dial in the redshift, look at the ratio here, and bingo, you have your extinction. So I'm just going to summarize. Measurement of prompt optical slopes, never done before, will really be a big help to understanding emission mechanisms. Measurement of the absorption frequency, in the case of synchrotron self-Compton, never done before, will give new information about physical conditions in the jet, including the radius of emission, a kind of mapping of these jets. Measurement of dynamic dust extinction, never done before, again, will solve that X-ray absorption mystery and allow us to study dust around a single star at huge redshifts. It's a very exciting prospect. So thank you very much for listening, and if you have any questions, I'd love to tell you.
Are there any questions? Yeah, sure.
You estimated the correlation time between Swift and your telescope as 16 seconds, yeah, as I remember.
So
the signal from Swift goes to the Earth and then to your telescope, and telescope find the point on the sky. So you said 16.
So the transmission typically takes 2 seconds, okay? And
no, I mean summary, some total time.
Yeah.
When your optical telescope find the point on the sky, so it's about 16, 20 seconds.
So the optical telescope will point in less than 8 seconds. If the optical telescope is pointing here and the gamma ray burst is there, there's 0 time to move. So the only time is 0 to 2 seconds. So it's between 0 and 10 seconds. 10 seconds maximum.
Okay. The question is, which is typical duration of a gamma burst signal?
So I'll go ahead and just show you that right there. So this is the Batsy distribution.
So about
of duration.
100 seconds, yes.
So the typical is about 20, 30, 40, about 50 seconds, right?
50.
The mode is 50 seconds, and then it's something the half both half max is something like 20 to 40
so
or 20 to 50
you
seconds.
hope to see something, yeah.
So we'll start measuring with 300 millisecond frames, 10 seconds after the burst. And so unless the burst is shorter than 10 seconds, we have a very good chance of catching it.
And how big is your optical telescope? 70 centimeters?
Yes,
I just
exactly.
didn't catch.
Exactly.
So, but you see that I believe it should be some mechanical vibrations because if you very quickly change your position, some proper oscillations and so on.
So it's really extraordinary how good these telescopes are because it's not that they're mechanically well constructed. No. They're smart. Okay, they sense some vibration and they correct for it in milliseconds. It's incredible. When I did the test, I did 10 times go across the sky and look. Okay, and I tried to make some kind of criteria for the telescope to stop so I could see it shake, and we could not do it. So the settling time, or the settling time plus the dynamic damping is within the 8 seconds. Okay, and in fact, it's so small it's within a fraction of a second. We were only able to see the image smear when we jumped on the ground next to the telescope. In fact, it's such a good dynamic system.
Okay, a few more jumps. Okay, next question.
First of all, Bruce, I think it's very exciting.
the science that is being proposed, I think, is really important and will go a long way toward answering one of the fundamental questions. Just a statement of fact. But now I come to question, a couple of questions, but brief ones.
Is your microphone on?
I think it is on.
Yeah.
So one question, you may have said and I missed it. Is the telescope already operating, or when is it going to start operating?
So we hope it will start operating within the next few months.
Next few months.
Yeah. So
Great.
the answer is that in detail, in fact, we believe the contract will be finalized in the next week, and then it takes a few months to get the telescope.
Okay, so that's a short time scale. Great. Two other very, very quick questions, and one of which is that in the picture that you describe is a very reasonable picture, and one complication that I see might happen is that there may be more than one component of optical at the same time, which is to say, in addition to the prompt optical emission coming from the same source that is producing gamma ray, you could have an extra component, such as a shock, external shock, that could also operate. So this is more of a comment, and maybe we can discuss this thing offline at some point. Yes. Last thing, and that is to do with polarization. I know that is much harder to do. I wonder, is that also part of some future plan for you or your group of people?
So I think as to your comments, generally speaking, there are so many conditions of gamma ray. Gamma ray bursts are so different. There's so many of them that it seems very reasonable to suggest that in a number of gamma ray bursts, one mechanism will be dominant. If it's not, then you'll see weak correlations in time and not strong ones. And so I think that won't work in every situation, but I think that'll help us if some part is correlated, some part is not correlated. And the other is to look at the slope and see, okay, if it looks like it. Another part of the question, the last part of the question was polarization. Okay, so the MasterNet has actually made some optical polarization measurements. For sure, you'd like a telescope that would do absolutely everything every time. Okay, but I think to start working on the emission mechanism, I think this is the most important, interesting thing to work on right away. I am always concerned about the polarization measurements because there are so many potential sources of depolarization. If you see a depolarized signal, a signal without much polarization, or as is more likely, a signal with a little bit of polarization, which is almost always the case, then you kind of say, well, it doesn't seem like a very smoking gun, a very strong statement. And the last thing I have to say is polarization measurements are incredibly difficult, not just because it's so difficult to calibrate these measurements, but because if you look into the actual details of polarization measurements, you need a signal noise of about 100 to make a good measurement of polarization to within a few percent. Because you got because there are 4 Stokes parameters and you need them all. Okay,
So we have one more question. Sure.
It's more a comment than question that I think you forgot to mention the association with the supernova.
I'm sorry? I can't quite hear you.
You forgot to mention the association with the supernova for the long GRBs, because in my talk for the short I will not mention that. So,
I'm sure I mentioned it.
Yeah.
I'm sure I mentioned it. Yes.
So okay, any more questions? No? So let's thank the speaker again. So now we have a coffee break. So we return back in 25 minutes at 3:15 p.m. 3:15.
So
3:15. So enjoy.
At maybe a millisecond frequency, is there an error in the tracking? Is there an error? Okay. Not only does it detect an error, but it detects a smart trajectory to optimally damp this. Okay, but But instrument controls working at a kilohertz, no problem, no problem. Okay, but now with a resolution of 10 to the 7, a fraction of an arc second, no problem.
And where is your telescope?
My telescope.
No, I mean your telescope. You talk about.
My telescope is currently sitting in the factory in Compton, California, waiting for the last signature on the contract.
I see.
Okay, and then when the last signature on the contract, it'll start.
It takes not less than 5 years.
No.
I mean putting this telescope on the